Right, recording started. As I mentioned earlier, this is topic 3, section 3, and the shear stresses in beam of the rectangle cross section is going to be discussed by today's session. And as you can see here, 2 seconds. Oh, okay. So now we talked about the pure bending cases. Okay, which means that you can see the cross section here, 단면, and the vertical stress is going to be applied. And as I mentioned earlier, all the video materials, assumptions are summarized here. You can read it, and then you can now clearly understand what I'm talking about. Okay, so this is the thing, the problem statement, and actual, and how to maintain the actual, the shape, so that we need some kind of, shear related component. Okay. So last time I talked about this one briefly, and that this is the equations that we derived before. We call the flexural formula. Simply, we also can say that this is the bending stress. That is the function of the applied bending moment. And here, y is the distance from the neutral axis. And actually, I is also learned from the statics, moment of inertia, second moment of inertia. So the left-hand side and the right-hand side, once we pick the small element from the entire beam, for example, this is the, the mid section. And then as you can see here, let me bring my pen. Okay, look at this one. So this is our, selected item structure, the tiny element, and definitely there is a length dx, and the left-hand side and the right-hand side, there is the moment and the shear components exist, isn't it? So that is left-hand side, the moment, and apply the shear is presented here, and the right-hand side, this is m plus dm, because we have additional lengths here. So this is v and m, and now I don't need to explain about the direction of the shear force, isn't it? To maintain the positive, so that it should be like that. So based on this, we will dive into the deep. This is the mid section, and then apply the moment. All the things are same, but the thing is, how to derive the equation. This part is, you can see this is like the free body diagram, isn't it? So from the left, stress 1 or stress left is applied, and this is stress right, isn't it? So we want to get equilibrium condition, and what we know is basically from this given information, we can set, okay, this is equilibrium force, and this is x direction, that should be 0, isn't it? So in order to meet that, we need to think about stress times area, that is definitely F, force, isn't it? So force 1 is applied to here, and force 2, opposite direction. And frankly speaking, F1 is not same as F2. We know that. And in order to meet this condition, like here, what we know is F1 minus F2, plus we need to get something more, F3. So which means that this term is going to be replaced by the shear force, blah, 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 isn't it? So I will move on to this. And of course, this is force is stress times area. In the case of area, that is quite simple and clear. It's like the rectangular section, so that we can get the information from width B and the height. BH is the area, isn't it? So we can focus on the stress, isn't it? So from this stress, you can think about this stress is like bending stress, that is moment Y over I. So we will bring this information, those two, to here. You know what I'm saying? Okay. So after that, frankly speaking, I talked about the F1 and the F2. Just simply substitute the flexural formula into these here, F1 and F2, and this is equilibrium condition. So F3 is F2 minus F1, so that you can simplify it, so that at the end, okay, we need to have one assumption. Look at this one. Shear stress tau is uniformly distributed along with the beam's width B. And from the video, I've highlighted on that. If the B or the width are too much wide, then it is challenging to adopt this. But in our case, we assume that the B is pretty much narrow. You know what I'm saying? Okay. So from that, I think you can get this information, and that this is first moment, so that we can simplify the equation. So basically, tau is V. What does it stand for V? Shear force. Exactly. So we learn about Vx is shear force diagram, and M, that was bending moment. So you can think two different ways, but not entirely different. So flexure formula, sigma, that was moment, y over I, isn't it? And one more set is needed for us. So the shear force is applied, and then the Q is actually first moment. Or you can remember, first moment, that was area times the distance, isn't it, from the neutral axis. So the other thing is I, moment of inertia, and then B, don't forget B is here. Okay. So you can think, oh, this is reason why they have selected these simplified, you know, the cross-section rectangle, because B is not changing, which means that it is much more simpler than the other shape of the section, isn't it? So based on that, we will move into the dip. Look at this one. So from this slide, we will get some information how to get these, you know, shear stress distribution, isn't it? So at the end, it should be available to get these equations. So frankly speaking, this equation tau is V over 2I and bracket blah, 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 like here. This is actually come from the original equation. Just now we talked about, what was that? Tau was V, Q, I, B, isn't it? So it really depends on the book types. Sometimes they use the F instead of the V. Sometimes they use the jet or something like different things, but you can understand this equation, the original meaning, the physical meaning. So based on this, we can remind our memories about the first moment, the calculation, isn't it? So y is the distance from the neutral axis, and integration dA means that is the definition of the area calculation, isn't it? So that should be 0 for entire, you know, area. So one important thing that is, if you want to calculate the Q, the first moment, and you can utilize this information. And the other thing, let us calculate the Q together. So this might be slightly tricky, but you can simply understand what I'm talking about. So Q is actually, what was that? Area times distance. Make it simple, isn't it? And then I have selected this shaded area, and based on this, we will look into the dip. So area, can you calculate this one? This is definitely B. And what is the height? Height component is h over 2 minus y1, isn't it? That should be different. So B times this height here. Actually, this one is represented here. So B, and this should be area, isn't it? Makes sense. And what else? What we need is this component, isn't it? So look at that. This is the distance from the neutral axis. Neutral axis position is pretty much clear. That is located here. And then this is a rectangle. That is very much fortunate situation. So that should be located at the center point, isn't it? So we are now only talk about the y direction movement. So that from here to there, this is actually the question. And what we have is y1 information. And just now we talked about this height that was here. So height over 2, that is this part, isn't it? So you can utilize this information over 2, bring it plus y1. That should be the total distance. We call the y bar, isn't it? So this is detailed elaboration. And then you can get this is like Q. Make it simple. Do the job, because this is y1 till here. They will integrate it using this information. You can get this way or that way. It doesn't matter. It's up to you. Okay. So anyhow, at the end, we can get this information. Now you can understand it. Just simply substitute this Q information to here, and then you can get this. Are you with me? Isn't it? So based on this information, the next step is pretty much simple. Look at this one. Let us think about the physical meaning of this function. This is actually shear stress. Is the function of the applied shear force. And from the section, we can get the moment of inertia. And the height is total height, h. It's simple information. And y1 is actually the main parameter, isn't it? So if the parameter is going to be 0, which means that this part will be the maximum, isn't it? So y bar is 0. That means here at the neutral axis, that is reason why we will get the maximum value of this shear stress. Or we can also think about the minimum value, which means that in the bracket, this value is going to be 0. That means the shear stress will be 0. In order to meet that condition, there is y1 value here. y1 should be h/2 or plus minus h/2, which means that this is plus h/2. This is minus h/2. So at those 2 points, we can experience the minimum shear stress. You know what I'm saying? And the other part is up to you. You can substitute something else like h/3 or like that, and then you can get all those values. Or you can simply use the MATLAB or the other software so that you can plot it. That will be like this one. Okay, that is clear. And let me compare. I like to describe like this way. So in the case of moment, the shear stress, what was that? Bending stress, shear stress. Again, flexural formula, isn't it? This is general way, and this is VQ over IB. And then it really depends on the sectional shape. So if the sectional shape is the rectangle, then we can get this value, isn't it? This equation. And one more thing is generally this bending moment, sagging or the hogging bending moment is applied, then we can experience like this kind of, the shape. Okay, you can simply plot this one. And generally, if the section is like that, the rectangle, then we can experience, and this is neutral axis, and this is the maximum shear stress and the minimum. That is for sure. I've mentioned about the shear stress as well as the bending moment till now. So they are talking about one more things here. So just now I mentioned about the maximum shear stress. In order to meet this, then we can simply y1 is 0. Then we can get 8i, VH square over 8i. So that will be like this one. So you can see that 1.5 V over A is, you can find it from the appendix or the design guideline or something like that. Okay. So this is the thing, assumptions. I try to show you the video, not to explain one by one. Okay. So remind the video material and then match it one by one so that you can clearly understand it. So what I want to talk to you here is once we apply the vertical load to our beam, this is the cantilever beam, then basically this is not behave like the simple beam theory because this is the mid plane. And once we cut the section, this angle that should be 90 degrees. That was the beginning of the simple beam theory, isn't it? But that is no longer available. That is the problem statement. As you can see here, the shape is going to be more than that. It's like, oh, this is more than 110 or 120 degree, isn't it? So effect of the shear that should be considered. Okay, so look at this one clearly. This is one good example, simply supported beam, left and the right, pin, roller, apply the distributed load is given here, 28 kilonewton per meter. And I have stressed on the unit that importance before. And then one more thing, the difference between the previous learning and the current is they have provided the sectional properties. And now you can link for everything. Oh, statics, free body diagram, apply the load, boundary condition, reactions, understand all the systems so that we can draw the shear force diagram, bending moment diagram. Shear force diagram, we can bring that specific value of the shear force. And then just now we talked about shear related functions here, isn't it? V. You can utilize it. And based on the given information, the sectional properties, you can calculate the Q, I, B, then you can get shear stress, isn't it? So I have now several options. I can change the sectional properties. I can select typical point, like here, from this point around 30 centimeter, okay? And then section around here from the bottom, calculate the bending stress as well as the shear stress. In order to get all those informations, you should follow the procedure that I mentioned earlier, isn't it? Okay, so all the details, I will not, try to solve all the details because you can get all the information here, the I, stress C, but at least you should try at least one time. Okay, and at the end of last class, I've mentioned about the concept of the safety assessment, like the capacity and the demand, isn't it? 자, 여기서 한글로 잠깐 정리를 하고 갑니다. 지난 시간 마지막 제가 뭐라고 이야기했죠? Safety assessment, capacity가 demand보다 커야 된다. 간단하죠? 그래서 어떻게 크냐? C를 그러면 간단하게 나누자. 그럼 1보다 크면 되겠네. 근데 여기서 대학원 레벨로 좀 더 넘어가면 uncertainty, 운송 중에 이게 파손이런 내부에 크랙이 있다든지 부식이 됐다든지, 그러니까 우리 구조물의 강도는 좀 underrated, 위험하니까. 그리고 외부의 하중은 100년파로 설계했는데 혹시 모르니까 1000년파 좀 더 외력이 크다고 가정해. 이런 세이프티 팩터를 넣기는 하는데요. 자, 이거 이야기를 했습니다. 자, 예를 들어서 여기 보는 거예요. 수지 응력이 지금 compressive load가 27 megapascal 압축력으로 작용을 하네. 그러면 자, reminder, mild steel 24 뭐라 했어요? 이 9.8을 곱하면 되지. 이 kilogram force라고 했죠. 그렇죠? 곱해보면 보통 한 235 메가파스칼 정도 나온다고 했죠. 그러면 딱 이게 뭐라 했죠? 이 뭐라 했죠? 이걸 알아야 돼. 일단 간단하게 생각하려면 재료 자체가 캐패시티입니다. 그래야 되겠죠? 그럼 이 말은 보통 학생들이 처음에 접하면 헷갈려요. 이때까지 다 계산한 거 구조 강도 아니야? 아닙니다. 그게 어디 가야 되냐면 자, follow me here. 오케이? 그러면 rearrange 해볼까요? C 자리에 235야. 보나마나 이제 안전하긴 한데요. 그럼 26.9. 이 부호는 상관없습니다. 이거 compression이기 때문에 마이너스를 붙여놨을 뿐. 그렇죠? 그래서 이렇게 해서 이 값이 뭐 대략 해보면 하여튼 뭐 1보다는 훨씬 크죠. 그렇죠? 그래서 이렇게 save 이렇게 해주면 좋겠죠. 그 세이프티 팩터를 근간으로 큰 거 봤지? 이렇게. 그렇죠? 자, 단면 1차 모멘트 뭐 이거 계산하는 것이 어렵지 않고요. 전단 능력 뭐 이렇게 하면 됩니다. 자, 이걸 왜 했냐? 제가 전단을 스킵하고 넘어가려 했는데 생각해 보니까 왜냐하면 전단은 보통 스태틱스에서 배우거든요. 근데 여러분들이 좀 지난 시간 확인해 보니 해야 되겠다 싶어서 한 거고요. 이 성분들을 다 했어요. 왜냐면 이겁니다. 이거. 이제 이 다음 스텝으로 또 제가 연결을 고리를 만들어 주기 위해서 이걸 했고요. 뭐가 보이죠 지금? 수직응력이라고 해서 26.9가 압축이 걸리는 여기 제가 가만히 있는데요. 이게 원셋이죠 압축은. 그렇죠? 26.9. 근데 위아래로는 뭐 땡기는 게 없어요. 그렇죠? 그래서 0 없습니다. 화살표가. 전단 뭐 구한 거 식대로 해서 전단식으로 전단 뭐 이거 기본식이죠 이거. 요거에서 구한 게 3.8 메가파스칼 파스티브니까 전단은 어떻게 해가 파스티브로 했죠? 우측하고 좌측 하단 여기 이렇게 잡아당기면 파지티브 반대로 이쪽 잡아당기면 그 네거티브라고 했죠. 그래서 요 우측 방향으로 요렇게 되겠죠. 이게 원 세트입니다. 요렇게 가는 게 세트. 요거 세트에서 파지티브 세트가 이렇게 걸려요. 됐죠? 자, 저 그림을 여러분들이 그릴 수 있어야 된다는 겁니다. 다만 이 내용은 지금 뭐 첫 번째 퀴즈에서는 안 나옵니다. 그 말은 중간고사에서는 나올 확률이 있다. 중간고사는 이제 범위가 처음부터 다 들어갈 거기 때문에 알겠죠? 그걸 무조건 알고 있어야 되는 거예요. 자, 넘어가겠습니다. 질문, question. No. So from here, this is like the additional applications. Just now we talked about the simple rectangle structure, rectangle cross section. And we need to investigate further. If the sectional shape is changed, what is going to be happened, isn't it? So they talked about shear stresses in the web of the beam with flanges. Just now we talked about the web. The shape is like the rectangle that we call the web. And on top of that, they attached some kind of flange structures so that shape will be changed like this, the H-beam, isn't it? It's up to you. As a structural designer, you can design our beam section like by filling all those volumes and then make like the volumetric shape. But the reason that we don't utilize that way is cost-effective solution is needed. That is too much heavy, expensive, isn't it? So this is also related to the moment of inertia. We learned that from statics. And you can look at this one, flange shear stresses and the web shear stresses. So before you start this study, I recommend you to go back to the video slide, the cut section, 15, 30, blah, 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 and junction. Okay. So look at that, the fundamentals. This is the schematic view. In Korean language, schematic view는 도식화를 한다는 거죠. 그렇죠? Okay, so now you can understand about this one, this shape. But don't be confused because suddenly I will go back. It was like that, the shape. And then what we learned before is the shear stress distribution is going to be like that. The maximum tau at neutral axis. One common thing is at neutral axis, different color needed. Neutral axis, tau maximum is still there, isn't it? But what happened here is they suddenly jumped into that level. isn't it? So this part, what happened? What happened? That comes from this junction because B is suddenly changed. We can remind our memories. Shear stress tau, that was V times Q over IB. B is suddenly shrinked, isn't it? So that the shear stress value, that should be dramatically increased, like here. So that is pretty much clear. Okay, so equations, I think that is not that much difficult. The calculation of the area, you can follow up A1, A2, and the Q, this one. This is a little bit complex, but what you need to remember is Q calculation, as I mentioned earlier. Once you calculate the first moment Q, we need to consider shaded area. That is the key point, not the entire section. That is reason why all the equations looks complex. But you can try at least one time, okay? If you don't understand this one, I will update the information. I will upload one more slide because in that slide, all the detailed derivations are included so that you can follow up. So in this class, I just want to mention about how to do that. The basic concept applications, you can follow up. Okay, so frankly speaking, all the things are actually here, but a few more things like the circular or the other shapes, I will provide the information. So in the case of web, you can calculate the moment of inertia. The one thing is most of the students, they can make some small mistakes from the calculation of the moment of inertia, isn't it? So be careful, AD scale, blah, blah, blah. I don't mention too much on that. But once you successfully get moment of inertia, at the end, exactly the same. Substitute it here. V calculations, this is actually come from the beam calculations. Beam's shear force diagram, bending moment diagram. Pick certain value, which means that, 자, 여기 집중, 잠깐만 할게요. 자, 이렇게 돼 있으면 무슨 말이냐면, 뭐 이렇게 하중이 막 가해지죠. 뭐 이런 하중도 가해지고, 뭐 이렇게 돼 있잖아요. 그렇죠? 제가 마음대로 어떤 특정한 위치에 픽을 할 수 있다는 겁니다. 그럼 shear force가 예를 들어서, 복잡하니까. 자, 다 지울게요. 이거는. 간단하게 이렇게만 해두고, 그러면 shear force 다이어그램이 이런 경우에는 그냥 이렇게 되죠. 뭐 이런 경우에 요 값을 여러분들 구할 수 있죠. 그러니까 요 값이 이제 요 특정한 이 지점에서는 x, 이 해당된 이런 빔에 가해지는 v가 어떻게 된다? 요 값이다. 그 말이고 그걸 들고 온 다음에 지금 요 계산은 이제 또 다른 이야기죠. 섹션에 대해서 지금 q하고 i를 구해야 돼. 그렇죠? 한 단계 이제 다운을. 그렇죠? 그래서 요거는 쉬운 거였는데 지금 ibeam 같은 경우는 요거에 대해서 지금 이런 식으로 i 값을 다 새로 계산을 해야 된다는 겁니다. 이제 i 계산은 i 계산은 전체 섹션, 크로스 섹션이고요. q는 shaded. 요거만 기억하면 돼. i는 항상 이 전체입니다. 전체. 알겠죠? 그거 한번 확인을 해 보시고요. Okay. I talked too much on that. Then at the end of the the equation, you can get this. This is like the the shape will be like small jump, and then like that, and then like this. So this part is made from the contribution of the B changes here, isn't it? So you can get minimum. In this case, there is a minimum shear. The top of the web, the connection part between flange and the web, that will be minimum, and the maximum definitely at the the neutral axis. So this is continuation. Please take a look at it. And this is the last slide. So you have any question on this?